So we'll start with the physics. What's the physical setup? And the physical setup here is it's a hydrodynamics problem in 2 dimensions, and it may be experimentally measured in a lab. One takes 2 glass plates and with a very thin gap between the plates, and one starts to pump. There's a viscous fluid between these 2 plates, and one starts to pump. So there's a viscous fluid between the plates, and one starts to pump a fluid of a much lower viscosity, or like air between between the plates, which displaces the high viscosity fluid. And what one sees is a sort of a bubble, and the bubble develops a very particular shape, which is fractal-like. And here's a result of an experiment with a very large bubble. And one sees like a tree-like shape with fractal properties then that one can study. Yeah. Length scale?
Yeah, what's a typical length scale that we're looking at?
Yeah, it's a meter, I know.
Oh, for the fractal-like thing, so these are like millimeter scale.
Yeah, so the smallest things can be, so it depends on the how fast they can pump the water in there, but they can be millimeter size or something like that, right? Because the faster you pump the water, the instability is stronger, and then you can see more intricate shapes. So, so that's the basic setup, and one of the fundamental question in this problem is to find out what, from an analytical view, what is the fractal dimension, what are the fractal properties of this fractal, and the main fractal description, the main parameter which describes this fractal is the fractal dimension, the box counting Hausdorff dimension of this fractal, which happens to be measured experimentally at 1.71. And that's still an open question, how to find out this fractal dimension of this object. And what I'll try to explain is how this problem may be linked to integrability, and it was shown to be integrable by people here in the audience. And the question is how to use this integrability to solve the problem, which I can't give an answer to, because I don't know how to solve the problem, but I will try to point out possible directions which may or not seem to you promising, but which I would like to suggest. That's at the end of the talk. Most of the talk I'll basically describe the integrable structures behind this problem. So let's see. So that was on the physics side. So let's see how to describe this Laplacian growth problem mathematically. So first of all, the very basic first part is to understand the hydrodynamics of the problem. Right. So there's a drop with a low viscosity fluid inside it, and it's surrounded by a high viscosity fluid. And high viscosity fluid, you may know Pouiseuille law. It's the usual law. If we have a pipe and it has a viscous fluid inside it, and we want a certain current of water inside the pipe, we have to apply a certain pressure differential to in order to make the fluid move. So this is the same law that we have in this for this Laplacian growth, which is in this context it's called Darcy's law, which states that the velocity of the fluid is proportional to the gradients of the pressure, which is basically Darcy's law within this context. So we have that the velocity is the gradient of the pressure field, and this will be important for the sequel. And inside the droplet, the low viscosity fluid, which displaces the high viscosity fluid, has hardly any pressure gradients inside. Simply, it obeys the same law, but since the viscosity is much lower, the velocity gradient become much smaller. So we can disregard any pressure gradients inside the droplet and assume simply that the pressure is constant inside the droplet, and outside the droplet, the pressure dictates the velocity in this manner. So this is the basic hydrodynamic setup for the problem. And we have incompressible flows, which means that the gradient, the divergence of the velocity is 0, which means since the velocity is the gradient of the pressure, it means that the pressure is a harmonic field outside the droplet. So we have a harmonic field P, which dictates the velocity. And on the boundary of the droplet, we have a constant pressure. We can set it without loss of generality to 0. We're only interested in relative pressure differences. So we have a harmonic field which has a Cauchy boundary condition on the droplet, which simply set it to 0 on the droplet. And the edge of the droplet moves according to the Darcy's laws, which means that the velocity of the boundary of the droplet is the normal gradient of the pressure. So this is basically the definition of Laplacian growth, right? So if we add to it a certain, that the pressure diverges as logarithmic of the distance at infinity, which basically says that we are pumping water out of the system at infinity. So, okay, so this is the setup. We have a harmonic field outside the droplet, a pressure which is 0 on the boundary of the droplet, and the droplet is moving according to the normal derivative of this pressure. So if we want to solve the problem, for example, on a computer, we solve this problem, a harmonic field which has this behavior at infinity and 0 on the droplet. We find the velocity. We move the boundary of the droplet according to the velocity a little bit. We compute the pressure. We compute the velocity, etc., etc. So that's the algorithm for solving the problem on the computer in this manner. And this is a definition of the Laplacian growth problem. Another fundamental property, or mathematical property of this system is that it's intimately related to conformal mappings. So since we have a harmonic field, it may use conformal mappings in order to find that solution of the harmonic field, right? So a harmonic field is the real part of an analytic function. And the analytic function that we use in order to find the harmonic field, so the harmonic field is here the imaginary part of some analytic function, which turns out to be the map from this cylinder, or from the region from 0 to 2 pi in the real dimension and infinite in the imaginary direction. The strip is mapped conformally, the upper half of the strip is mapped conformally to the outside of the droplet. So this mapping, or inversely, the inverse map is phi of z. So this is z of phi is a mapping from here to here. Phi of z is the mapping from here to here. And the imaginary part of phi of z on the boundary of the droplet is 0, because the boundary of the droplet is mapped into the real line. So the imaginary part of this map is 0, like we want. This phi is the analytic function. Its imaginary part is harmonic. So P is indeed harmonic if we define it in this way. And we can check that the boundary conditions in infinity are also that it goes like logarithm of R. So this is basically a solution of the problem of finding, boundary problem of finding the harmonic field P. Okay, so in this way, you can also solve the particular problems analytically. You can start with a certain shape, say a circle or an ellipse, etc. Find the harmonic map, the conformal map to this half strip, and then see that you can then advance the boundary of the domain, and then for successive time find again the conformal map for each moment in time, and in that way solve the problem. And in this way, you can solve particular examples of the problem, like an ellipse. There's a circle is solved. There's a certain Joukowski map, which gives you and certain shapes that are exactly solvable by this method. Okay, so that's one thing about the mathematical properties of the problem. There are certain exactly solvable cases. But a general initial value problem is hard, but you can still use this map. You can find this map numerically. and you can solve also the initial value problem numerically using this conformal map technique. Another important property of this problem is that it is integrable, which is related to the fact that an infinite number of conserved quantities completely prescribes the solution. So if we find there is a certain conserved quantities inside the evolution, which are called Richardson moments, that completely prescribe the evolution, and we can use them to solve the problem, and they connect up the problem to integral systems. And these are given in a following form. They're called Tn. That's the nth Richardson moment. It will not change within the evolution. To see that, you can use the conformal maps or other techniques. And it's defined as the integral on the exterior of the domain of z. Z is the complex parameter to the power minus k, integral d squared z. Right? And there's also the complex conjugate of which is Tn bar, which is also conserved. So they're complex parameters which are conserved. And the question, one can ask whether one can show that this is formally an integrable system, namely that we can find an infinite number of Hamiltonians in some sense that commute amongst themselves, and a certain Hamiltonian prescribes the evolution of the problem. Okay, so yeah, so this thing doesn't move. Yeah. Okay. Oh. Okay, sorry. So the conserved quantities suggest that the problem is integrable, and this was shown. The fact the integrability was shown by these people in 2000, and then further paper in 2004. And the basic idea is to think about this conformal map Z of phi. So as you remember, phi was this variable. Z of phi is a conformal map from the strip to the exterior of this droplet, and it's also a function of time. And we can think about this function as a dynamical variable, which we want to write an equation for. And we prescribe a Poisson structure, which says that phi and t are canonically conjugate. So we think about phi and t as canonically conjugate variables. And and now one can write an infinite number of conserved quantities, hk, as equal to the plus part of z to the power k. So you take the map z and raise it to the power k, and then expand this z to the k around infinity in e to the I phi in this manner, and take the plus part, namely throw away all the negative powers of e to the I phi, and one gets a certain function which one treats as a Hamiltonian, kth Hamiltonian. And the point there that there are an infinite number of them, and they're all in involution. They are Poisson commuted with each other. If we take phi and t to be the canonical variables, canonical conjugate variables, and so and in this way one can also define deformation of z, treating each one of the hk's as a Hamiltonian. Right? So hk can be treated as a time translation operator with respect to tk, and tk was the appropriate Richardson moment. So if we want to change the shape, we want to change the shape of the domain such that only one of the Richardson moments is changed. So this is dz to dtk. One takes the Poisson bracket of z, which is a conformal map from the half strip to the exterior of the domain, and takes a Poisson commutator of the z with the kth Hamiltonian, which is defined in this way. And this is this define an infinite number of conserved quantities, which are now hk, and for tk we understand now as the appropriate times, right? So tk's are actually the times, and hk's are the conserved quantities. And one can show that this equation holds, meaning that it's indeed, these are indeed in involution. That's a zero curvature condition, which is usual in integrable systems. Okay, so, and one should also comment that there is a constraint here. One can show that z and z bar is the you take the conformal map and take the bar over all the coefficients. The Poisson bracket of those two is 1. Actually, this is the what prescribes the evolution in real time, right? Because if you look at this equation, this says nothing about the evolution in real time. This equation, which comes in the form of a constraint, actually prescribes the evolution in the real time and not in the Richardson moment times tk. Okay, so this is the integrable structure of this of the problem, and there are certain special features in terms of how integrability comes into the problem, which are kind of different than usually, and what we usually expect in integrable systems in their application to physical problems. And let me just go through some of these special features that are particular to Laplacian growth, at least. So, first of all, something that I haven't mentioned is that the problem is actually ill-defined. So if we start with this system that I showed you in the beginning and solve it, we see that with that the droplet develop cusps. So the initial value problem is ill-defined because a singularity occurs in the solution, and this is solved physically by the fact that there is surface tension, which I have neglected in defining the problem. So what surface tension does, it will cut off any singularity in the shape of the droplet. Any cusp that we may want to form would be cut off by the surface tension. But the surface tension will destroy the integrability of the problem. So this is one problem that is with the integrable description of the problem, is that it always hits a singularity. And another peculiar thing that I'll talk about later is that the integrable structure is a certain dispersionless limit of another integrable structure. We can think about these Hamiltonian as some semi-classical limit of a system of quantum Hamiltonians. And what I'll talk about later is the fact that these two problems, they solve each other, right? So the problem is ill-defined. If you look at the quantum system that for which this integrable structure that I showed before was the semi-classical limit, then this problem turns out to have no problem with singularities. So we have to one way to solve the problem of the singularities is to regularize the problem by basically looking at the quantized problem, the quantized integrable problem, and working with that problem, which will solve for us the problem of the singularities. And another problem another feature of Laplacian growth that in a physical sense, what I've mentioned before, is that we're interested in the factor dimension of these growing clusters. So we're not really interested in the initial value problem. We're not really interested in solving particular examples or for simple initial conditions. We're more interested in random initial conditions and asking what is the most probable fractal dimension of the resulting cluster. So this is a sort of statistical mechanics problem that it seems that integrable systems is not very adept at solving, and we have to find certain certain methods and ideas in order to apply integrability theory into to the problem in order to also describe the statistical mechanics of the problem. So in this sense, what I will talk about at the end of the talk is a further quantization of the problem, which may allow to address statistical mechanics questions, such as the factor dimension. But this is the more speculative part of the talk, and I will see if I'll get to talking about that towards the end. Okay, so so the first thing that I mentioned is that the problem is a sort of a semi-classical version of a quantum problem, which and this quantum problem has no issue with singularities. So to understand that, I have to introduce this notion of semi-classical limits in integrable systems, which is intimately connected to dispersionist limits and something called Whitham equations, etc. So let me just describe what that is in the context of integrable systems. Right? So if we have a certain integrable system, let's take the qKdV equation to be concrete. And we want to solve it for some initial condition, which are very smooth. If the initial conditions are smooth, we can imagine that the higher derivatives are smaller with respect to the lower derivative terms. So this term in the equation is rather unimportant, for at least at the initial stage of the evolution. And we may want to solve simply u dot plus ux equals 0. And simply drop this equation, right? So what we will get, if we solve u dot plus ux equals 0, is we have some initial conditions. And then what this equation prescribes is that points that are higher move faster, which means that the wave gets steeper and eventually overturns. And so this is the basic property of this equation. It produces this singularity. And at the singularity points, this point, and that point, the derivative becomes infinite. So obviously the approximation that we took was inappropriate, and we should rethink what really happens. What really happens is once this wave gets steep enough, when this term is present, is that instead of an overturn, as we see here, what we get are a set of oscillations. Right? And we may ask, how can we solve the problem with these oscillations, using similar ideas that led us to drop this term in the first place. So obviously we cannot throw away completely this term, but we can still may ask, suppose I put an epsilon in front of this term, what happens as epsilon goes to 0? Right? We can ask this question, which is a similar similar problem to simply ignoring this term. So what we observe is when we let epsilon goes to 0, that this oscillation become tighter and tighter. So the frequency of the oscillation becomes higher, the wavelength of the oscillation becomes smaller as epsilon becomes smaller. And this limit, in the limit epsilon goes to 0, what we can do is we can keep track of the envelope of these oscillations, right? So since the oscillation becomes so high frequency, we can look at the oscillation, define some sort of envelope for this oscillation, and try to write an equation for the envelope, for the how the amplitude of these oscillation changes in both space and time, and how the frequency of the oscillation change in space and time, etc. Right? And so the idea is, this is the idea of the Whitham method. And how to describe this oscillation? So since we decided that we are going to describe this oscillatory regime of the solution, we first have to notice that this is actually nonlinear oscillations. So these oscillations are very rapid, and they are prescribed by the full solution of this equation. So these are like oscillatory solutions of that equation. And what we want to do now is kind of characterize these oscillatory solutions, or parameterize these oscillatory solutions of the qKdV equation, for example. So how to do that? So to do that, we make use of some of the integrable structures underlying the qKdV equation. And most prominently is the existence of a Lax operator. In the case of the qKdV equation, we have a Lax operator, which is simply the usual Schrödinger Hamiltonian, where we take for the potential the solution at a given time of the qKdV equation. And what's special about doing that is if U satisfies the qKdV equation, the spectrum of this Lax operator, which is here just a Schrödinger operator, does not depend on time. So we may draw the spectrum of this operator, the which is given here, for example. This is, if I choose a certain U, this may be the spectrum of this Hamiltonian, given here. And this spectrum will not change for steady oscillations, because it does not change for any solution of the KdV equation. So what this allows us to do is to take oscillatory solutions and look and try to see how its spectrum looks like. So it turns out that if we take an oscillatory solution of the KdV equation, what we see is a spectrum which has a gap in it, a single gap. So for example, suppose we have this solution of the KdV equation. There is a global spectrum for the whole solution, which I'm not drawing, and it's very complicated. But I can look at the spectrum which I get if I locally isolate a certain region where I have very fast oscillations, and imagine that these oscillations do not change in amplitude, in phase, in frequency, etc., that they are just steady oscillations. If I plug this steady oscillation into this Hamiltonian, I will get a spectrum which has a certain gap in it, and the position of the gap and the position of the endpoints of the spectrum will completely describe the characteristics of these oscillations, namely their amplitude, their phase, their mean value, etc. So I may describe each area of these oscillatory regime in the KdV equation. I may characterize it by a certain spectrum, which is a spectrum which I will obtain if I will imagine that these oscillations are steady and do not change shape and size along the x or t direction. And what we get then is a slowly moving spectrum as I move across the solution. Here I have a smooth solution, so I have a spectrum which doesn't have a gap in it. Here oscillation starts, so the gap forms in the spectrum. It moves and then goes to zero again when the oscillation's amplitude goes to zero. So this is a sort of a description. And one can write equations for this, for the endpoints of the gap. And these are called the Whitham equations. Yeah. So it turns out that Laplacian growth is in some sense this equation for the endpoints of the gap. So it can be mapped into the equation for the endpoints of the gap of a certain integrable system called the two-dimensional total lattice equations. And the total lattice equations are the full equations, the full integrable equations. They have no singularities in them. And the equations for just the modulation of the oscillations, which are the equation for this a certain spectrum associated with the Lax operator of the two-dimensional total lattice, are the equations of Laplacian growth, which seem to have some sort of a singularity in them. Okay, so the Lax equation, the Lax operator of the what replaces this Hamiltonian for the two-dimensional. So here we had this Lax operator for the KdV equation. Now we have a much more complicated Lax operator, which is a huge matrix of this form and can be written in this way. But the idea is the same. One takes this operator, finds its spectrum. The spectrum is invariant in time, and this defines for us a certain the Laplacian growth problem. So let's look at this correspondence, right? So there is a full equation, the two-dimensional total lattice equation, which is the full quantum problem, and there is this semi-classical limit, the Whitham equation, or dispersionless limit, which is Laplacian growth. In the two-dimensional total lattice problem, we have a Lax operator, which has this form, a certain complicated matrix. And its semi-classical analog is a function. So an operator becomes a function because the Whitham problem, or the Whitham and dispersionless limit, is a certain semi-classical limit. So operators become functions. And this function is z of phi and t, the conformal map. So the Lax operator in the semi-classical regime becomes the conformal map. Then the time, which appears also here, has there's a conjugate operator, which forms a Heisenberg algebra with t, which is just a derivative with respect to t. This derivative with respect to t goes over to phi. And we have the Poisson bracket in the semi-classical limit of phi and t equals 1. And in the two-dimensional total lattice, we had Hamiltonians, which are produced from the Lax operator by taking the kth power of the Lax operator and taking the plus part. In a similar manner, in the Laplacian growth problem, we take the kth power of z, as we already have seen, and take the plus part, we get a Hamiltonian, etc. So these are the two, this is the analog. And the semi-classical limit is basically what I've described before, is this fact, what these equations describe are basically the slow motion of the spectrum of the Lax operator under this Whitham equations, which are the slow modulations of oscillatory solutions of the two-dimensional total lattice equations. Okay, so that's, and what this allows us physically is, okay, so let's also look at how this, the shape of the droplet is affected by this motion. What's the relation between the evolution of the shape of the droplet to the evolution of the spectrum of the Lax operator? So suppose we take this KdV solution. Turns out that the KdV equation appears, or the KdV integrable structure as a whole, appears at a certain limit of the Laplacian growth problem. And this is the limit where we concentrate on a certain small piece of the full droplet, a very sharp and narrow piece, a finger, a very long finger of the Laplacian growth. Here is the boundary of the droplet drawn in red, and inside this boundary of the droplet there is a certain branch cut of say the conformal map or some combination of functions which are related to the conformal map. And this branch cut is actually the spectrum of the Lax operator in the quantum regime. So inside the droplet there lies some sort of branch cut, on which we also have the spectrum of the Lax operator in the quantum regime. And as we describe this KdV flows, which describe also this finger moving in time, what we see is that we create a certain another support for the spectrum, and around this support of the spectrum there will be another piece of the boundary of the original Laplacian growth problem. So what we see is that, and this allows us to, this whole evolution is integrable in the sense that there are no, first of all, that this is a solution of the KdV equation. No singularities are formed. Actually, they are avoided by the introduction of this new droplet. So if I would continue to solve the original droplet, I would get a singularity. But what this quantum analog teaches us is that in order to avoid the singularity, we have to introduce another disconnected piece of the boundary in this point and allow this to evolve. And the full evolution is then, of course, for both integrable and regular. And yeah, and yeah. So in terms of physically, what this means is that we allow independent positions another droplet to form within the helical cell, which is impossible in the regular helical cells because this is a glass container which doesn't allow air to. So this is air and this is oil. We have to allow for the creation of additional air bubbles within this the helical cell, which, for example, may be obtained if instead of a glass plate, we put something which is permeable to air, and which will allow another air droplet to grow. So that's a certain regularization of the Laplacian growth problem. Okay, so that's how integrability comes in. We see that the evolution is actually on the spectral surface of some integrable system, the 2D total lattice, which is somewhat unusual. The physical growth is not on what is usually taken to be the physical surface, but it's on the spectral surface of some operator, which is kind of unusual For example, in the KdV problem, we looked at the evolution here in real x and t, but the evolution of the Laplacian growth problem happens on the spectral surface of some operator related to this solution. So this is one takeaway from that, and the second is that the problem may be regularized in this manner. Okay, so let's talk about the remaining issues that are still open then. And the remaining issues are, of course, related to the main open problem here, which is the fractal dimension of the droplet. So fractal dimension of the droplet displays itself in the fact that the area of the droplet is proportional to the radius, the size of the droplet, to some fractional power, which is the fractal dimension of the problem. And we want to try to understand that. And we mainly want to see whether we can use the fact that there is certain conformal invariance in the problem. So we're used from statistical mechanics, from equilibrium statistical mechanics, that conformal invariance is very helpful in finding scaling laws, the value of scaling dimensions. And that's because conformal invariance shows itself out in the field theory description of the problem by the fact that the system may be described by conformal field theory. And in conformal field theory, the way that conformal field theory helps us to find these fractal dimensions or the scaling laws of the problem is that it allows us to obtain a discrete spectrum of scaling dimensions. So the representation theory of conformal transformations as it is applied in conformal field theory allows to find a discrete spectrum for a possible fractal dimension. And the natural question in this field is now whether we can use the same tools to find the fractal dimension of the Helly-Shaw droplet. This is the only tool available to finding exact. Either the problem is free, or we may use the representation theory of the conformal group of transformations, the quantum group of transformations, what's called the Virasoro algebra, to find these scaling laws. And there are no other tools actually in our disposal. So the only reasonable method, one can arguably the most reasonable method to try to find this fractal dimension, is to somehow to connect the problem to conformal field theory. And we may hope that that is the case, that they are related by the fact that we've used a lot the idea of conformal transformations in solving the problem, at least classically. And the question is also, so we have conformal field theory and we have integrability. We should ask ourselves whether there is some combination of integrable structure and conformal structure that may help us to solve the problem, the Laplacian growth problem, and find the fractal dimensions. So a certain suggestion that we may offer is that one may look at the quantized version of the qKdV equation in order to make this connection. And then the next question we can ask is, beyond the formal relation of the quantum qKdV problem to the Laplacian growth problem, is in what sense can we, what kind of objects in the quantum qKdV equation may describe the fractal dimension of the Laplacian growth problem? So the Laplacian growth, first of all, as I've mentioned, has a qKdV limit. If we take a droplet and look at a certain part of it, which is very long and thin, that part of it is described by qKdV. It's a certain limit. We said that the whole droplet is described by the two-dimensional total lattice. But the two-dimensional total lattice has a limit in which it becomes qKdV. And this corresponds to zooming in on a part of the droplet, which is very sharp, very narrow and long. And and qKdV has an intimate relation to conformal transformation. This is why this limit may seem appealing. And okay, so I've basically talked about that. Okay, let me skip that. Okay, so let me explain how the KdV problem is related to conformal transformations. So in order to write down the KdV equation, we have to pick Hamiltonians and pick a Poisson structure. And one of the Poisson structures that may be used in order to define the Hamiltonians that describe the KdV problem is this Poisson structure, namely the function u, which is which solves the KdV equation at different points in space, will have this Poisson relations. And this actually Poisson structure is intimately related to conformal transformations. So, for example, if we in quantum theory, if we want to apply conformal transformation, we use something called the stress. We use the stress energy tensor, which happens to in conformal field theory happens to apply conformal transformations in the following way. So suppose we want to consider the following conformal transformation. It's the identity plus a small part which has a pole at z naught. And we want to apply this conformal transformation on some operator f phi. Namely, we want to look at phi not at the original point z, but at the new point f of delta z, which is this conformal transformation, and see how it changes with respect to the original phi at the point z. So we take phi at this new point minus phi at the old point. So we apply this conformal transformation. And we want to look at the difference, that's delta phi. It turns out that we simply can insert t, the stress energy tensor, in any correlator, and this will apply the exact same transformation. So namely, t of z is the generator of such transformations. So we can think of t as a generator of conformal transformations, and then we can ask what is the commutator of t's at different points, which will define the algebra of conformal transformations. So this commutator defines the algebra of conformal transformations, and it turns out to have this form. So we see that the commutator of conformal transformations has the commutator has the form which exactly repeats the Poisson structure of the KdV problem. And this means that we can treat the conformal transformations as a stress energy tensor as a quantization of the KdV field U. This is the connection between the two problems. And in this way, one can also define Hamiltonians. So in KdV, we define commuting Hamiltonians by taking the field U and taking certain combinations of that field U. The first one is the momentum, the second one is the energy, etc. And we may try to find certain commuting Hamiltonians also in the quantum case by just guessing them from their form in the KdV case, in the classical case. And since the Poisson structure of the KdV is so similar to the commutator in conformal field theory, what we get is simply that these Hamiltonians do commute. So we are able to find an infinite set of commuting Hamiltonians in the quantum case, which quantize the commuting Hamiltonians of the KdV case. And so in this sense, we have quantum KdV as a quantization of classical KdV, or conformal field theory as a quantization of classical KdV. Okay, so that's the quantization, but then we ask, okay, so that's we quantize the problem of a very thin and narrow, thin and long finger, and we got conformal field theory. And then the question we may ask is what kind of object we may look for in conformal field theory, which may describe the statistics or the probabilities or an ensemble of solutions of the Laplacian growth. So which will have this fractal property, this scaling property. So in that sense, we may look at spectral expansions. So what is a spectral expansion of an operator? So suppose I have a certain operator from conformal field theory, the quantization of KdV. I may apply it to the vacuum to get some state. This is some state which is associated with the field phi. Then I may do a spectral expansion. Namely, I may expand it in eigenvalues, the common eigenvalues of all these Hamiltonians. So all these Hamiltonians commute. They have a set of common eigenvalues. They may be found in the beta ansatz. And we may expand any operator with a set of eigenstates of the Hamiltonians. And the eigenstates are a solution of beta equations, and in fact, they have a relation to the spectrum I've shown you before. So in the semi-classical limit, the beta roots of this, or the eigenstate of this equation, are characterized by the same spectrum that I've discussed before of the Lax operator. And in that sense, what I've done here, I've taken the operator and expanded it in states which are characterized by a spectrum of the Lax operator, which also means that they are characterized by certain shapes of the Laplacian growth droplet. So basically, it's an expansion of a conformal field theory states in shapes of the Laplacian growth problem. So this is kind of offering us some sort of a statistical mechanics object. We take in a state, and then we have an ensemble of shapes of the Laplacian growth problem, which characterize this shape. And in fact, okay, so what we'd look at is so this amplitude here, a phi 0, kind of is the probability amplitude of finding any one of these shapes of the Laplacian growth problem. So in fact, what we will do is we'll think about the absolute square value of this probability amplitude as a probability of finding a certain shape of the Laplacian growth problem, and this will define for us an ensemble of shapes, an ensemble of Laplacian growth droplets, and this is will be the object we will want to think about in the quantum settings. But the question is, what operator should I put here, right? So this is an expansion of any operator. And the question, what sort of operator should I put here in order to get a fractal, a growing fractal, an ensemble of growing fractal of the Laplacian growth problem? Right? So a natural suggestion is to take one of the scaling fields of the problem, right? For in any statistical mechanics problem, in equilibrium, we're familiar with the concept of scaling fields, which describe they're very familiar in renormalization group, and there's the same field which are conformal fields or descendants in the conformal field theory settings. And the basic property of these fields are their scaling variance. If I take the field at alpha x, this is the same as the field at x. So I do a scaling transformation of space. It does nothing to the field phi except multiplied by a factor, and this factor is the scaling that alpha that I introduced to some power h, which is the conformal dimension of the field phi. And these h's are actually have a discrete spectrum in conformal field theory. They are constrained to have discrete values. And these are what allows us, for example, to solve statistical mechanics problems in equilibrium. We know that there are certain discrete values that any scaling field can take, and these are the only fields that we will encounter in solving the problem. So we take the same scaling fields that allows us to solve the problems in equilibrium statistical mechanics, and produce from them a certain probability amplitude, which is given in this way. And we may wonder whether the scaling behavior of these fields carries over to the scaling expansion to this P of A. So it may be argued, this is not established, that the following is true, that if I describe this as the probability of finding this shape of the Laplacian growth, then the radius, the size of this of the shape, will scale with the area of A to the power h. So So this relation holds. So the argument is that this equation also specifies this form, which already already suggests a fractal pattern for the states which support this probability distribution function. And the other property that may be argued is that this probability distribution function is time independent. Namely, if I advance a certain shape in time, according to the Laplacian growth evolution, it will have the same probability as the one that was not advanced in time. So this basically means that indeed the probability distribution function thus defined, at least according to this argument, which I haven't shown, is indeed a probability distribution function which describes an ensemble of growing fractal clusters. And the fractal dimension D is simply this H. And depending on the conformal field theory, which is appropriate to describe the problem, we get a discrete set of possible fractal dimensions. But all this is, of course, speculative. This is the part that I said in the beginning would be speculative and not fully determined, but this at least is some sort of direction in which one can hope to employ to combine the conformal invariance properties of Laplacian growth with its integrability in order to get information about the fractal dimension. So let me summarize. Okay, so the summary, we've seen that Laplacian growth is a certain semi-classical limit, also called the dispersion limit or Whitham limit of the two-dimensional total lattice equations. To limit this two-dimensional total lattice equation become the qKdV equations. The qKdV equation, in order to get a statistical mechanics theory, may be quantized. And this quantization leads to conformal field theory and a statistical mechanics description of Laplacian growth, which holds a promise, at least, to allow us to find the discrete spectrum of possible fractal dimensions for this problem, which is, of course, the holy grail of this field. But this is still very far from being established. This line of research, but this is just a suggestion for a possible direction of study. Okay, this is it.
Yeah. Conformal field theory, the way we know it, is applicable to equilibrium statistical mechanics, successful theory. Now, this problem is out of equilibrium, and the system has a flux. It shows conformal symmetry, perhaps, but it also has a flux. This thing keep growing. Mm-hmm. Similar story in two-dimensional turbulence. The conformal field theory seems to be applicable, but in addition, there is a flux. So it must be a serious modification and an unknown, undetermined modification of conformal field theory to adjust it to problems out of equilibrium, but steady with a flux. So the question is, and this is another version of the same general issue, how to apply conformal field theory, not to equilibrium problem, but to stationary, steady problem with a flux. And there are many examples. Turbulence is one, this is the second. So what I'm missing is you seems to be using the standard setup of CFT, which is, where is the flux there?
No, so it's not, I mean, usually you don't look at this object in the usual setup of CFT. First of all, you just take this operator phi, work, and this X is in the real space, the real physical space, right? So this goes to the same point that I was making here, that there's the right. So there's so there's this space, and there's this space. So here there's normal. You can do normal CFT here in X and T space. That's statistical mechanics, and you look at certain objects which are simply phi of X is a local field of the theory. And here you have to do physics here, right? So the suggestion is that that these two problems cancel out each other. The fact that you have non-equilibrium and you working over here mean that you use different objects, and they may now be applicable also out of equilibrium. Namely, in particular, you'd never look at the spectral expansion you never look at the spectral expansion of some operator and say, okay, this is my probability distribution, because usually the spectrum is a completely auxiliary object. Here it's the physical object, so you look at this object here, and it's a completely different setup. So this is not the usual way you apply CFT to physical systems in equilibrium. That's one issue, yeah. And then the second issue is that the parameter that I'm looking at is here, right? It's I'm running over all spectra of it's like a soliton expansion. So I have a conformal field. I apply it. There's a state. There's a operator state correspondence. I have solitons here. I can expand the state into solitons. This is my A, and now I interpret these solitons and every configuration of solitons as a Laplacian growth pattern, and look at that as an ensemble of Laplacian growth shapes. And since the field is conformal, or it's a scaling field, then I would get fractals here in terms of the solitons in the spectral surface. So it's a very different way than equilibrium. Equilibrium in physical space. This is non-equilibrium on the spectral surface, so it's not the same thing. Yeah. H knows about A. No. No. H comes from here, from the operator. Regardless of A, yeah. So this is but once you fix this operator, this probability distribution function may be supported on only certain A's. So the A's that are supported by this probability distribution function may depend on H. From a different equilibrium problem. Yes, it's the same, but the point here that is deducted from the conformal algebra, right? So there's a certain C, there is a certain spectrum of H's, and it's not that it will be shared by equilibrium problem, but both are deducted. The common feature is that they're both a consequence of the conformal algebra.
Any other questions? So I had a very naive question. Could you just explain a little bit in detail how do you get the spectrum?
For which case?
When you were talking about Whitham equations.
Whitham. KDV still.
Yeah, KDV. Just what is? I mean, what do you exactly?
Here already.
Right. What exactly do you? I mean, so this is the oscillations that you get when epsilon is very small, right?
Yeah. So there are these oscillations, say, and then I blow up this thing and I see steady oscillations.
Okay.
And then basically I continue them as if they don't change.
Okay.
right? And then I take this thing, take this U and plug it over here.
Okay.
And find the spectrum of this Hamiltonian.
Okay.
And this is what I'm drawing, the support of the spectrum. So the spectrum has a gap.
I see. So do you have to carefully choose the windows, or doesn't matter?
Doesn't matter, no. So
because some of the windows seem bigger and some seem...
No. That's not, there's not windows. This from the internet. I don't even know what's these numbers.
Okay, so okay. Any further questions? For a nice talk.